Today, we're diving into the secret identities of the chemical world. We're talking about how a single element can show up in forms so radically different you'd swear they were completely unrelated. They're like the shapeshifters of the periodic table. So let's just jump right in with a question that sounds kind of like a riddle. How can a flawless, priceless diamond, one of the hardest things in the known universe, and the cheap, soft tip of a pencil be made of the exact same element? It seems impossible, right? Well, the answer has a name. Allotropy. And it's a really cool idea. All it means is that an element can arrange its atoms in different patterns. You've got the same building blocks in the same state, like they're both solids, but because the blueprint is different, their physical properties are worlds apart. This is the secret key to our diamond and graphite mystery. And that, of course, brings us to our most famous shapeshifter of all, carbon. I mean, it is the ultimate example of how just tweaking the design at an atomic level can lead to completely different outcomes. Here's the thing you have to remember. It's not what it is, but how it's put together. Think of it like playing with Legos. You can take the exact same set of bricks and build a super strong, solid cube. Or you can build a flat, flimsy wall that falls apart. For carbon, that atomic blueprint is literally everything. Let's really look at that blueprint. So, in a diamond, every single carbon atom is locked into this super tight 3D grid with 4 of its neighbors. It's what makes it unbelievably hard. And notice there are no free electrons floating around, so it can't conduct electricity. But then you look at graphite. The atoms form these flat, hexagonal sheets, kind of like layers of chicken wire. And those layers are held together really weakly, so they just slide right past each other. That's why graphite is soft and slippery. And get this, each atom has one little electron that's free to move around. That's why it can conduct electricity. It's a total game changer. And these properties, of course, directly affect how we use them in the real world. That incredible hardness of diamond, perfect for cutting through rock. The slipperiness of graphite makes it a fantastic lubricant. And its ability to conduct electricity is why it's a key ingredient in things like batteries. It all just comes right back to how those atoms are arranged. Okay, so let's switch gears from carbon and look at our next element, hydrogen. Now with hydrogen, the differences are less about physical form and more about, well, its chemical personality. It can have 3 totally distinct levels of reactivity. I love this quote from our source material because it paints such a vivid picture. It talks about a newly born hydrogen atom. Just imagine that. A hydrogen atom that's just been created in a reaction. It's in this really temporary, high-energy state before it's had a chance to calm down. And that has a name. Nascent hydrogen. So you can really see the 3 personalities here. First, there's molecular hydrogen, or H2. That's the normal, stable stuff all around us. Pretty chill, not very reactive. Then you have nascent hydrogen, that newly born atom that is just itching to react with something. But the most extreme version? That's atomic hydrogen. Single H atoms that only exist at crazy high temperatures, and, get this, for only about 1/3 of a second. It is an incredibly powerful chemical agent. And you might think making this super reactive form is really complicated, but it's not. It happens in a really basic lab reaction. You just drop some zinc into sulfuric acid, and the reaction starts freeing up individual hydrogen atoms. For just a split second, before they can find a partner and form stable H2 gas, they exist in that nascent state, super reactive and ready to get to work. All right, for our last stop, let's talk about an element that none of us could live without, oxygen. Just like carbon, it has 2 famous allotropes, but their story is all about life and protection, from the very air we breathe to the invisible shield protecting our entire planet. 10 parts per million. Just think about that number for a second. It sounds like almost nothing, right? But that's the tiny concentration of ozone high up in the stratosphere. And that incredibly small amount of this special form of oxygen is pretty much all that stands between us and the sun's most dangerous radiation. So here are the 2 faces of oxygen. On one side, you've got dioxygen, O2. That's the good stuff that makes up about 21% of the air we breathe. It's what powers our bodies. But on the other side, you have ozone, O3, a molecule with 3 oxygen atoms. Down here, it's actually toxic, but way up in the stratosphere, it forms the ozone layer, which is basically our planet's sunscreen. So how is this incredible shield even made? Well, it's this beautiful, self-regulating process. High-energy UV light from the sun, the very thing we need protection from, zaps an O2 molecule and splits it into 2 separate oxygen atoms. Then, one of those free-roaming atoms bumps into another O2 molecule, and they team up to form O3, which is ozone. Isn't that amazing? The danger itself is what creates the shield. Okay, so we've looked at three elements with multiple personalities: a diamond and a pencil, a stable gas, and a super reactive atom, the air we breathe and our planet's sunscreen. So why does understanding this whole idea of allotropy actually matter? What's the big takeaway? Well, it matters because for carbon, this shape-shifting ability gives us everything from the sheer beauty of a diamond to the simple utility of a pencil. And it doesn't even stop there. We're now using this exact principle to create revolutionary new materials like graphene that are pushing the limits of technology. And when it comes to hydrogen, understanding its different reactive states is absolutely key to controlling chemical reactions. Whether you're trying to create fertilizers to feed the world or develop new clean energy sources, knowing which personality of hydrogen you need is critical for scientists and engineers. And finally, oxygen's dual nature is just fundamental to our existence. The tiny difference between an O2 molecule and an O3 molecule is the difference between the energy in our cells and the protection of our entire planet. One single atom changes absolutely everything. So the next time you pick up a pencil or just take a deep breath, maybe think about the hidden complexity in the elements all around us. Allotropy shows that even the most basic building blocks of our universe have these incredible, surprising secrets. And it really makes you wonder, if one element can hide this much, what other wonders are out there, hiding in plain sight?